So now let's look at what is available in scikit-learn in terms of clustering. So we have Kmeans. So Kmeans is directly implemented in clusters.kmeans. So the parameters, we have n cluster, which is specifying the number of cluster, the value of k to use. We have a maximum number of iteration, which is by default 300, which should be quite enough. Usually we are able to converge fast with Kmeans. But the thing is, we are often making use of repetitions with Kmeans because Kmeans, we have no guarantee. There's no guarantee that we will reach the global optimum. We may be stuck, and that depends on the initial points. We may be stuck in some local optima, which is bad. Basically, we don't want this. But this may be relatively, I would say, not rare, but this is not the usual case. We often converge to good solutions depending on the dataset. I think it depends on that. So a way to avoid getting one bad results through bad luck of bad initialization, we will make repetitions. So we will repeat the same clustering from different random initial starting points using whatever method as soon as it is random. And we will keep the best of these, for example, 10 repetitions. So we will make 10 repetitions, 10 times running Kmeans with different starting points, and we keep the best of these 10. This would avoid the cases where a bad initialization will lead to a bad clustering result. And that helps a lot to get Kmeans with nice results. Also, the initialization can be different things. There is the Kmeans++ for integration approach that can be used. Just specify this, or random for random initialization using an ND array for the given values. We can just give directly the initial values that we want to use if we have some specific approach for that. And then we have some tolerance to on the initial before declaring convergence, just to be sure that we are tolerating some variations. And the results that are encoded in that class, somehow we get this cluster centers, which is an array with the value of mi, and we also have the labels, which is the bit, and some initial value, which is I would say, something quite close to the reconstruction error. We also have mixture models for EM here. So we have, I would say, mixture.Gaussian mixture, where specifies still the value of k, the number of components. And then we state the covariance matrix. We can get different covariance matrix, either the full one or the one with shared covariance or the one with a diagonal covariance or spherical. These are all possibilities, and the maximum number of iterations that we will use. And the number of repetitions with the best solution is kept. So that's kind of possible, along with the initialization method, where Kmeans is kind of a good starting point for that. And the results will be the weights. So prior probabilities for each cluster, the PGI. And we also have the means, so the mu I somehow, and the covariance matrices. Depending on the type of covariance matrix we are using, it will be available in there. And then we also have the hierarchical clustering functions in scikit-learn. So we have agglomerative clustering. So we start with the number of clusters to find. Basically, we can go just to up to 2 clusters. Sometimes you're saying 1 cluster doesn't make sense because, it's just putting all the data together. So we will stop at 2. So these are like 2 final clusters. But we will have all the possibilities from n to 2, basically, clusters in our model. We can use also some kind of affinity, which can be Euclidean, L1, L2, Manhattan, cosine, pre-computed. So by default, it is Euclidean. And we have the linkage approach, because the affinity is for the point-to-point distance, and the linkage is from group-to-group distance. So by default, it's what we call a ward here. It's kind of minimizing the variance of agglomerative clusters, but we can have complete linkage or average linkage. These are all possibilities. And the attributes in the end will consist in the labels of, so all clustering is done in terms of labels, the number of leaves in our dendrogram. So when we see maybe up to n, but maybe we would like to start before if we don't care about, if we think it is that useful to go through n different, I would say, so this is a result basically. So this is according to our dendrogram. we also have the structure of the dendrogram, which is given in children. So this is relatively complex, but a way to represent the dendrogram, the kind of tree that is turned on the side that correspond to the results of our agglomerative clustering.